first of all, Varuni. I'm part of the same AI/ML team. Though I do also work on scaling of these AI/ML workloads on the traditional supercomputers like Aurora and Polaris that we have at ALCF. Um, a lot of my time goes in also exploring these new noise hardware accelerators, which we call as ALCF AI Testbeds. So these are systems from different vendors out there. They're all AI startups, traditionally designing a new hardware architecture for these AI ML workloads. So I'll be kind of giving you an overview of what these are, how does it differ from the traditional GPUs, and also we'll have like a hands-on to see how easy or difficult it is to use these test beds, because most of the people here would be used to kind of programming a GPU or a CPU in that nature. So just looking at the evolution of the systems that we've had in the ALCF, currently, of course, from the last few years, we have the NVIDIA A100 GPUs and Polaris. And then in 2025, our flagship supercomputer Aurora, which has traditionally the Intel GPUs, went into production. But over time, these systems are designed much in advance to when it is kind of deployed. And we had all these surprises in maybe early 2020 or late 2010s, where, of course, the AI/ML atmosphere completely overtook all the workloads, and a lot of people were running these large models, which could not get the good compute performance on these traditional GPU computers. That's when I think the ecosystem changed in sense of trying to build these hardware accelerators that are more kind of conducive for running these AI/ML workloads. So from around 2020, we started acquiring a bunch of these new accelerators, which we'll talk about. And over the time, we have built new system, added new vendors, and so on. So primarily, of course, we have the experimental facilities like APS, which kind of have these experiments going on, and you kind of need real-time inference. Also might need some offline training to kind of analyze the different images, which essentially are like quite high resolution in nature. And also it does take pretty large models to kind of converge for these kind of workloads. So traditionally, we use our supercomputers here at the ALCF, which does, so the data is essentially streamed from APS. You kind of do all your workloads, whatever you're trying to solve the problem, and then you kind of stream back your results to this facility. So when people started to analyze these kind of AI workloads, especially for these kind of high resolution image kind of workloads, we also try to use these accelerators and see how does it kind of benefit these kind of large image workloads and so on. So our ALCF AI testbeds, it's kind of an infrastructure, you can say, where you have multiple of these different vendors. They're all optimized for different metrics in some sense. And we have a bunch of them over here over the years. We've tried to analyze the performance and benchmarking of all these accelerators for the different workloads that usually people tend to have in the AI/ML workspace. Our overarching goal at the end of the day would be to say, how does these accelerator perform when compared to our traditional GPUs? Um, and beyond that, if you see in the future, you might have all these heterogeneous systems, and you would essentially, because your workloads are now becoming, kind of heterogeneous, you need different accelerators to kind of be adaptive to these workloads. So understanding how these accelerators can coexist, maybe within the rack, or uh, maybe somewhat complementary to the other CPU, GPU kind of architecture, is what we kind of foresee to be in our future systems. So we have systems that we differentiate with respect to the kind of workloads, at least that they can support as of now. Is for training, we have both Cerebrus, the CS3s. It's at the moment under acceptance test. We just upgraded from the second generation to the third generation. We have the SN30s from Sambanova. So we have around 8 racks of them with 8 nodes in each of the racks. So the GPU equivalent in Sambanova is kind of called as RDU. It's just called as reconfigurable data flow units. And on Cerebrus, we have like 4 third generation Cerebrus wafer scale. For people who don't know or haven't seen a Cerebrus wafer before, it's almost equivalent to the size of my screen of my laptop, or your dinner plate, if that's what if it's more easier to understand. It's one of the largest made chip until now, and it has around 900,000 cores of compute on a single wafer. So these two systems are um, meant for training. And we also have acquired lately a bunch of inference-only systems, in which the Sambanova SN40L, which we call as Metis in the ALCF, is a next generation or a fourth generation of the Sambanova systems that's particularly very inference-driven hardware. We also have the Grok, which is again an inference-only systems. We have one rack of that which has traditionally 9 Grok nodes, and each node technically has 8 Grok chip, or which is also called as tensor streaming processors. And then the Cerebrus CS3s are also configurable to do both training as well as inference. But of course, the inference stack is still naive. It's under development. So we assume by this year end, we will have the complete inference infrastructure up and running. In addition to these systems, we'll also coming up with the Tens torrent. We'll have 2 racks of Tens torrent that will probably come up by this year end. And each of these, or combining the 2 nodes that we will have, which is the Galaxy unit of Tens torrent, will have like 32 wormhole units, or technical equivalent to whatever GPUs you call on other platforms. Of course, these systems, to a large extent, can do, or at least attempt to do, the traditional HPC workloads. In that sphere, especially Cerebrus and TensorRent have put considerable effort in kind of driving these kind of workloads. This is just like a snapshot of the different specifications. One important aspect that I want to highlight is on CS3s, you have like 44 gigabytes of SRAM, along with like a memory X, which is kind of equivalent to, you can say, as DDR. And that's a configurable one. So for training, you use weight streaming, where essentially whatever is your limit of your memory X, that will drive what is the maximum model size that you can perform training on. On in the inference side, it's a little different. You kind of have model parallelisms where you map out the model across different chips to do some tensor parallel processing. On Samba Nova, SN40L at least, it is like a 3 tiers of memory where you have, again, a huge SRAM availability. Then you have an HBM, which almost has 64 gigabytes. The difference between the previous generation of SN30 versus the SN40L is the fact that you have this additional tier of memory, whereas of the HBM, whereas the SN30 never had the HBM per se. The DDR, like the external DDR, almost remains the same. Well, not almost, like 1.5 times the previous generations. Um, but other and the other one to note is these mostly provide software stack supporting PyTorch, but of course it's kind of packaged in its own its own custom package that it comes from. As I spoke before, the HPC software ecosystem also exists on these AI accelerators, though it's at a very naive state. But Cerebrus software language, which is the HPC ecosystem of Cerebrus, and even the one from Tenstorrent, have considerable presence in the user community. Okay, so I've been talking a lot about these systems, but in general, how do they compare with the data flow kind of architecture? How does the data flow architecture compare with the traditional GPUs, if you may ask? The traditional GPU-based system has like this one-by-one kernel launch, which kind of takes in a lot of this launch times, which was kind of expensive. Whereas on the data flow architecture side, you will see that like you can map each of the model using its compute graph, and you can easily lay out or map each of these kernel onto the wafer, and you'll mostly these elements that you see are called compute units, and most of them have like different names on each of these vendors, but essentially each of them have a compute and a memory that's kind of coupled together. I think that's the most like stark difference kind of between the traditional GPUs versus the data flow architecture, where you have the memory kind of etched or coupled very close to the compute unit, so that you don't have too much of communication that you need to do, and essentially you have very high memory bandwidth. So like you see, the simple convolution graph here is kind of mapped onto the wafer here. So on the right side this is a particular example of Samba Nova architecture, but again, in philosophy, it kind of applies to most of these systems. So you kind of map each of the kernel graph onto those PEs or PCUs, it's called, which is programmable compute unit, and it has essentially its own memory, which is the program memory unit. So this way, the data flow will kind of eliminate the launching of kernels, and also kind of eases the memory traffic that you'll traditionally see in the GPUs. Again, like said, the left-hand side is the Samba architecture, where each node has like 8 different RDUs, and each RDU has 8 different tiles. And you can see that if you zoom in on the tiles, you'll have this interconnection of PMUs and PCUs along with the switches for the communication. You'll kind of see a similar systolic kind of array in the Cerebrus architecture as well, where it's called as a PE, or programmable element. And the difference there would be that the data only flows from kind of the way it's shown, either from left to right or up and down. Um, or yeah so each of the element can only communicate in a single clock cycle to its kind of neighbor on its side, or below, or up. um, and if you can zoom in on the programmable element over there, you will see like a processor, scratch pad memory, as well as the router that's configured into that P. So long story short, there are two main probably concepts of data flow architecture. Of course, this is not something new. This has been in the ecosystem quite for a while. So having these compute and memory units close together obviously will enhance your memory bandwidth. And data just flows through these compute units without kind of having to get back the intermediate states of the computations. Of course, each of these accelerators have their own tools, very similar to how NVIDIA has. But of course, it takes a while for these kind of systems to kind of mature. Okay, as part of the ALCF AI testbed, we try to engage with different user communities, try to, we have tutorials at several supercomputing and international supercomputing conferences. We do have extended trainings annually from our facility. So we kind of, since these are naive accelerators, you kind of, and is always changing with respect to the hardware generations as well as the software stack. It is on us to kind of educate the user. So we kind of have, it's open for all. So anyone can attend these trainings and kind of use these accelerators. So if you ask how to use these accelerators, there are three kind of different ways to do that. Of course, one is for most simplest one is the director's discretionary. This kind of has all the allocation request links and so on. All you need is to submit a proposal, why you need and what are you going to run on these systems, and you can get access to any of these systems. There's also the NAIR, which is a NSF DOE kind of initiative. Several researchers across the universities also get access to these systems using this program. Of course, all the information that I have shared or links to the other detailed informations are all available in the AI testbed user guide, which is on our website. So this is the Argonne, the LCF website, and if you go through, you have the AI testbeds over here, and you have a detailed information of how to access the systems, the overview of the systems, and how to even like port and run kind of a guide for anyone who is new to these systems. So we've kind of gone through how, like, what are these systems, and just to give a flavor of how we've used these systems, these are some of the examples. Of course, you can, we've we've been able to port a lot of science models, both text-based and vision-based. So some of the examples, if I can show, is one of the um, Gen SLM, which is kind of a precursor of mprod DPO, is the one where you use a language model to identify the variant of concern, or in specifically in this case, we use the SARS-CoV virus, which was kind of a huge thing back then around 2020. This particular research was kind of the winner of the ACM Gordon Bell Prize for 2022 under the um, COVID-19 research track. Essentially, we used a large language model, or LLM. Of course, we pre-trained them from different sized models for large sequence lengths. And we scaled this on GPUs, the Cerebrus CS2s back then, and SN30. So if you can see the performance, the throughput that you get, of course, from the CS2s and the SNs are much higher when compared to the throughput that you can get on a A100 node. But beyond that, it's also the energy efficiency of these systems that will be helpful in running these large models as well as large context models where your input is very large. The other kind of example I can say is the drug discovery, where you can use a BERT model and you can easily get a 3x speed up when compared to a traditional GPU on a Grok node here, without any kind of optimization done on the ASIC side. So beyond the training, a lot of these vendors now have moved to the inference sphere, where you can see that the throughput and the latency that you can get for most of the common Llama 7 billion, 70 billion, DeepSeek, whichever models you see, the Saminova and Cerebrus have a very high throughput, low latency kind of they beat the GPUs in most of these metrics, especially with kind of the utilization that you have on the GPUs. Again, I'll kind of skip through this. The other one, most importantly, we see is the weather forecasting. I know Sam talked about a lot about the Aries, which is a newer version, but there was an older version of the Aries that used a transformer kind of model. And we also do these weather forecasting on these kind of machines, where you can see that all the code on that, like kind of the kernel schedule for the GPUs, it is all done using just one, and just not on the one layer. So the entire, say, a transformer from the layer one, which is the embedding, to the final, which is depending upon if it is the classifier or any other kind of modeling, you have all those mapped on to the wafer, and there's just like one kernel call, which kind of takes care of all these compute, and you get the final answer just from the hardware. You don't have to do any optimizations with respect to moving the data, kind of sharding, especially which is what you see on the flash attention kind of kernels in the traditional GPUs. We also use these kind of accelerators for doing some live inference on the APS data, which is kind of what is shown here, where you use the accelerators to do real-time feedback. But then again, you also capture all these logs, and you can do an online training on the HPCs that you have on ALCF. Uh, Again, we've also used these accelerators for the traditional HPC kind of workloads, where we've got like 100x speedups with some of the Monte Carlo simulations or even stencil kind of calculations. Uh, of course, these are, you know, new systems. They're always good and bad about things. I mean, we always, people complain about the GPUs maybe like 20, 25 years back, which is where we are with respect to the accelerators, AI accelerators in today's world. So overall picture, they're very energy efficient. They are good to deal with very large inputs, a high resolution or even like large context lens. Traditionally, because they have very high SRAM. So that's where these kind of accelerators are very different to the traditional GPUs. They are good for low latency critical applications. And most of these systems have off-the-shelf models for the inference workloads. Again, there are room for improvement, of course. Porting these models is not easy. It does take some time and effort to do so. But again, you have to choose which workload is critical and use that effort in the right way. And the other one is the compile times. All these traditionally, these are kind of FPGAs, if you want to think of it. So you need to program the FPGA, which means you have to compile the graph, lay it out uh, on the fabric, and it takes a huge toll on the compiler. And to build such an ecosystem is not simple, especially for the AI workloads, which keeps on changing over time. And it's very fast paced in nature. Of course, there's also like room for improvement with respect to the tools that these systems offer. And we would hope to see more HPC coverage so that you can use the same system to do kind of traditional HPC workloads as well as the AI surrogates for all these science applications. So this marks the end of the overview of AI testbeds. But I definitely wanted to kind of do a hands-on to just kind of give you a flavor of what it looks and how do we really program or how do we run kind of these systems. Um, some of them you probably might not have access, but again, it's pretty easy to request access. You have the DD allocation, which I went through before. But again, you have all these information on the ALCF HPC workshop GitHub repo, so you can just follow through with all these kind of material. All the links and everything is available in this particular channel. Of course, this is I'm just one of the person who works on these systems. Again, there are many other in my team who also work here, so it's kind of you know a group work, if you can say that. So I just want to take through about Cerebrus. So Cerebrus, if you see, is the so we have these four CS3s. So you can SSH to these systems using like how you do it on say Polaris or Aurora. You have a login node as well as a compute node, and when you and you essentially log on to these systems and connect to the management node. It has an internal Kubernetes kind of scheduler that will schedule one of the idle CS3s when you kind of get a job. The one good thing about these systems is you don't have like a typical scheduler that you see on like PBS or Slurm, where you have limited time. There's a queue where you have to get through. So if you have like simple models that are like you're taking off the shelf kind of training, or even doing inference workloads, I would say if you can hop on to these systems, and so once you hop on to these systems, you have it until your job completes. So you're not preempted per se like you do on the other systems. So if your workloads are simple, you don't have to scale for a large number of nodes. But again, mind you, you can also do a lot of compute that you do on multiple nodes on say Polaris or Aurora, that you can all condense in a single kind of node, or even the compute unit for these systems. Um, so like I said, you log into the login nodes and then you hop onto the user node or a compute node. So you also have like how to kind of uh, issue a job, which can be again like if you go through the Cerebrus kind of PyTorch implementation, you have it's a simple virtual environment that you have to create. The steps are very clear and concrete, and then you also have some of these kind of models repository that they kind of support. So if you, I've just moved to the Cerebrus GitHub repo here, and like you see under the language models, you have a large set of models, the usual llamas, mistrals, and the older ones like BERT and so on. So these models keep getting updated every kind of release, and you can kind of use them to train. But if you can go into the system, so this is just like I have logged in using a terminal, using those SSH instructions. And if you can, like, let's just go through kind of like an example here. So if you go to the Llama 3.8 billion on the Cerebrus compute node, you first kind of like activate the virtual environment. And for each of the model, you have a YAML file that pretty much has all the configurations that you need to run any model. So if you kind of look at this is a YAML file for a Llama 3.8 billion, where you say first the trainer arguments, like where's the data, what kind of processor you need to do required for the data processing. And then, of course, these are very similar to the PyTorch ecosystem that you see. You mentioned what kind of number of workers that you need, the shuffling, and so on. Uh, Apart from that, you specify CUDA or XPU on the other systems. You have the CSX equivalent here on the Cerebrus. And also there are some, kind of the micro batch that you can specify, the gradient accumulation and so on. And of course, the checkpointing. Again, if you see the other main part of this YAML file is the model configurations. So essentially you can, so each of these, broader level architectures of models like Llama or the T5 and so on. Here it's a Llama example. So you can take this and modify your own, hidden size or your layer norm or whatever it is. And then you can bring up any transformer, easily by changing this YAML file. All changes go into this particular file. Then you can specify of course, the optimizers, the precisions, and schedulers, and so on. So this is most comprehensive configuration that you can find for all these transformer-based systems. And the way to run is pretty simple. So you just copy this YAML file, do whatever changes you need for the configuration, and this is the standard kind of uh, command line argument that you use to run this, which is the CSZoo. And if you fit, this is the kind of API you get, and you mentioned the YAML file. That is essentially what will start running compile your model first, of course, which you can see here is I've done it prior to this. So it'll just compile for all, like you see, it's compiling the model. So there is, for training, you also have this memory X, and you also have the activation servers that kind of streams all your data, your models, your weights, and so on. So yeah, and then it'll it'll compile, it will program your fabric, and you can see all the type of net oops sorry network that it's using, and this is where you see the different training epochs. I've just done it for like 10 steps, but of course you can choose your own number of steps. So this is what you see for, I think this is the 8 billion model. So yeah, I don't remember. I think it's somewhere, if I'm not wrong, like um, 20 seconds is what it takes for, I think, similar thing on for one iteration on a GPU based system. So uh, yeah, you have very high kind of throughput here. That is essentially how you run things in Cerebrus. Um, so this is a training example. Um, and you can, of course, have different models that you want to do. Next up, I just wanted to show the Sambanova SN40L Metis. So this is a new system that went into production maybe like a couple of weeks ago. So this is the fourth generation of Sambanova systems, typically only used for inference workloads. Again, you have so one good point of this is even you don't even have to log on to the system to kind of use this. It's like any OpenAI kind of chat completion API that you'll see everywhere. So it's compatible with that. So it's very similar to what you do with an OpenAI API. So the way to go about this is how to access the API key. So currently we have like two systems or two nodes, which have 16 RDUs each. So you can refer to the website here under the Metis inference about the different informations. But essentially, at the end of the day, you need to log on to the Sambanova login nodes where you will have the two endpoints configurations available to you along with your API. So once you get the access to the Sambanova, you go to your Sambanova node, which is what let's do this. So yeah, you have so you have Metis endpoint kind of one, which here you see is it gives you the base URL. You have the Sambanova API key for which is again your own key, and it also specifies which models is there. Currently, we have models DeepSeek R1 on the one of the endpoints, and if you see a similar one, you will see Llama Maverick on the second pod, if you may call us. So all you need to do is just kind of source this file here. If I want to just do, oops, 0.2, I just source this, and you export these environmental variables, which is essentially the model name. Say I'm just going to use the Llama kind of Maverick here. And then these are coming from your sourced kind of file. Um, yeah. And then you can just use either like a Python script, like the way you do for OpenAI. You can use the same kind of script here, or you can also use a curl command to do the same. So just if you kind of copy this template here. You can use it for any of your chat completion. So I have this chat completion here, which is essentially your OpenAI key and so on. So you just get your key and your OpenAI URL and the model name, and you use the OpenAI client to just get the response. So, for example, if I just even copy paste this, um, yeah, so it used this URL, it used this model, and this is the prompt that I gave, and this is what it kind of gave you the answer. You can of course do all this similar with respect to the curl command and all the kind of you can also use multiple prompting source, which kind of gives you the effect of how a chat GPT is kind of used in the backend, where there are multiple users and all of them are kind of blasting their prompts onto your inference engine. You kind of collect them. All of these happens in the backend. You don't have to deal with it. It kind of queues it, and it uses different batch sizes for each of these models. Of course, they have to be configured with different batch sizes. So yeah, and you can service concurrent requests for these APIs. So this is kind of where do we stand on time? Okay, we are doing good. So like I said, if we go to this AI testbeds, we are done with an inference system. We have seen how we can train on Cerebrus. On Sambanova SN30, you can also do training. A similar kind of architecture with respect to how you access the nodes, where you log in to the Sambanova login, and then you go to the different compute nodes. So those instructions are kind of given here. Just to kind of like walk you through like a unit example, you can see that there are kind of some scripts, if you see here, um, to kind of like one is the compile and second is the run. Um, for simplicity's sake, I'll just go through the compile command. So if you go through the script, you have this is the compile command, right? Like, so you have a Python compile.py, and then you have to mention that it's a compile, and this is a unit. So you just give the number of channels, your image sizes, your batch sizes, and kind of like, so the concept on Sambanova is a little different when compared to, say, Cerebrus or other systems, where like Aurora, each of the RDUs, or in Aurora, you have each GPU can be again kind of bifurcated into two tiles. So similarly, Sambanova, each RDU can be bifurcated into like 8 tiles, which you can program kind of individually. So this particular workload takes up like 4 tiles, which is like half an RDU. So essentially on a node, you can have like 16 instances of these workload in parallel when you're running in a DP kind of fashion. So yeah, so you just provide the PEF name. PEF is what the intermediate compile artifacts that you generate as part of these compile process. That is essentially will tell you which compute graph will go where on the fabric and how each P is configured and the output of which P goes to which other P. So all the network routing, all the compute kernels, the inputs where it has to draw, where the outputs has to go, everything is defined in this PEF that is kind of generated. And that's what you use. So once you get that PEF, you kind of, oops, sorry, you pass it to the run command, which is what you're seeing here So you're using the run, and also you provide the PEF that you just kind of generated. Yeah. So you provide the PEF wherever you specified as the output file in the previous command. And if you do that, you can run the same on multiple instances of this system. So that kind of covers the Sambanova training, Sambanova inference, Cerebrus training. Cerebrus inference will also be, as I told, will be up and running in a couple of months. It has a very similar kind of look and feel of how we went through the Sambanova Metis kind of OpenAI chat completion API. Um, so these are the kind of more newer systems that we have had and upgraded. There are, of course, also the Grok and the GraphCore. Unfortunately, these systems have kind of like died down in terms of availability, also depending upon how the vendors have performed over in the ecosystem. Um, but we do have TensTorrent, which is a RISC-V, so fully open sourced, very similar to like how NVIDIA had it like the few decades back. So we are going to have the Galaxy systems installed on the ALCF infrastructure in a few months. So I hope you can kind of get a flavor of how to use the systems and how different they feel when compared to programming a similar GPU CPU systems. Um, yeah, any questions? Happy to take that. I know it's a lot of information, so feel free to get access to it and go through it in your leisure. And overall, we're seeing that more and more users are kind of using these systems and trying out for their AI workloads. And we are internally exploring how we can use these systems as part or partially or fully integrating it into our larger flagship machines in the future.
Any?
I am new to the term accelerators. So what is the main difference between the different accelerators and mainly like the ones that are used for the AI and the one ML?
Okay.
And the architectural differences, perhaps.
So traditionally, it's how your compute, there's always like your compute, your communication, and your memory, right? These three are the three pillars for any architecture. So where each of them are placed, like how close, what's the memory bandwidth is one, what's the compute bandwidth is one, and third is how much of memory you have will define what kind of workloads you can run on a single GPU and how you can scale out or scale up depending upon what infrastructure you have. So when compared to the traditional GPU architecture, right, like the one that we went through in the first few slides, where the compute is different and memory is different. So you're always having the challenge of moving your data from the HBM to the SRAM, where SRAM is almost in kilobytes. And that's how traditionally it's been. It's been a little up over the generations, but nothing really too different to what you have on these systems. These systems have a very, very high capacity of SRAM in their systems. Some may be very high, like say Sambanova, which has like around 520 gigabytes of SRAM in its fabric. And of course, there are also other DDRs and like different hierarchical memory or structure of memory that's introduced. But traditionally, if you see over like why these came into first of all existence is like, as I said, in around when AI ML workloads were all like getting out of hand. This is again in when it was going in millions. Now it's in billions and trillions of parameters. But traditionally, people didn't want to do all those communication because uh, AI workloads are communication intensive, right? You have a lot of backprop that you need to do. So there's a lot of all reduce that's happening. And with larger models, which means you're like say 8 billion llama, for example, you have so you're essentially, communicating all the gradients from different GPUs. So now you have like, whatever you use like 10,000 nodes of Aurora, then each of them are communicating the same amount of 8 billion, say, gradients, and you're accumulating all of them. So your network bandwidth has to be like really large to accommodate such a kind of workload, right? So you do not want that so obviously it's compute heavy, it's communication heavy, and you are low on GPU memory. So all these three were kind of challenging, especially for training on these systems. But then the so that's where these kind of accelerators started coming in. But over time, it's also the fact that a lot of the industry has moved from like training to inference as well. So inference needs low latency, right? So these kind of systems which have very high and efficient memory bandwidth can do that. Like they're more conducive for such applications um, uh, than compared to the traditional GPU base, where you also have an extra software ecosystem that you need to build if you're going to like scale up or scale out in terms of your workloads on these computers. So that's the main difference in terms of like you know uh, overall, like 1,000 feet view. But again, there's a lot of intricate details or differences between each of these architectures. There's Each one has its own philosophy and how they do it. But most of these accelerators have that goal, in the sense they don't want to have too much communication. They want to have larger models localized onto like a single compute unit, compared to the GPU counterpart. So that's where these accelerators, especially when you have very large um, very high uh, input, um, in terms of resolution or in terms of your context length or whatever. You want, so these are able to, because they have high SRAM, now it's easy for you to have both a large model and a large input to coexist in the similar kind of, and you can have better utilization when compared to a kind of GPU. So in tense torrent, like I've seen, like they have, if you do a gem kernel, for example, you almost can reach up to like 70 to 80%, or even 92% of utilization on tense torrent compared to the traditional GPUs.